Hello and welcome back. In last video, we defined the notion of sequential continuity, and we defined continuity before that. I'll just remind you the setting. So we have a function f that goes from a metric space to another metric space. We have a point in M, and we say a function is sequentially continuous at this point P of M if, give me a second, say sequentially continuous P if for any sequence we have, if we apply our function f of x to the sequence, we land in f of p. So that's called being sequentially continuous at a point. And we say continuous at p, U-O-U-S, continuous at p if for all epsilon greater than 0 there exists delta such that the distance between p and x is less than delta. That implies the distance between f of p and f of x is less than epsilon. So in this video, we want to show that these two notions of continuity are in fact equivalent for a metric space. So what are we going to do is we're going to prove continuity implies sequential continuity first, because that's the easy case. The other one is also easy, but requires a little bit of thinking to prove that sequential continuity implies continuity. Let's do the easy one first. So assume continuous. So continuity implies sequential continuity. Okay. So we want to prove something is sequentially continuous. So that means we want to show that if we pick any arbitrary sequence, let x and tend to p be arbitrary sequence, in M, we want to show f of x n tends to f of p. Now we have to use the fact that x n tends to p is a sequence, and we also have to use the fact that our function f is continuous at p. So how do we, okay, so we want to prove that f of x n tends to f of p, and then in order to prove that a sequence converges to something, we have the usual epsilon n definition. So let epsilon greater than 0 be arbitrary. We want to show that if we go far enough down in our sequence, then f of xn is epsilon close to f of p. So how do we do that? So first of all, we use the fact that our function is continuous at p. So that means there exists delta such that whenever we have any point in M, thus delta close to p, then we are epsilon close to f of p, f of x is less than epsilon. So we just have to go far enough down so that all the points in our sequence are like delta close to p, then the thing on the right would automatically be satisfied. So because xn tends to p, we have some natural number m such that n bigger than or equal to m implies the distance between these points and our point p is less than delta. But then that implies that the distance between f of xn and f of p is less than epsilon. So in other words, if we have any natural number bigger than or equal to m, we have f of x and this sequence converges to f of p, which is what we wanted to show. So we have continuity implies sequential continuity. I am going to copy the definition of continuity and sequential continuity for the other direction. Let me go to next page. The way we are going to do this is via contrapositive. So we will assume that our function is not continuous at p, and then we will show it's not sequentially continuous at p either. So here's how it goes. So that's the definition of continuity. For all epsilon greater than 0, something is satisfied. If we assume our function is not continuous at p, then that means there exists epsilon greater than 0 for which the thing on the right hand side is not satisfied. Okay, what does it say on the right hand side, the thing that's satisfied? It says that there exists delta greater than 0 for which something happens. The opposite of that would be there does not exist any delta bigger than 0. So no matter what delta we choose, we will have that this thing implies f of x less than epsilon will be false. So this being false means the thing on the left hand side will be satisfied, but the thing on the right hand side will not be satisfied. So if something implies something, the opposite of that would be yes. Even though the condition happened, the consequence did not happen. So that would be this, but the thing on the right hand side did not happen. Bigger or equal to epsilon. And this will be true for no matter what delta we choose. So let us choose delta equals 1 over n. So 1 over n is a natural number. And then for each n, there will exist at least one xn of f of which this will be true. Okay. So now we have assumed our function is not continuous. Now we want to show that our function is not sequentially continuous at f of p. So how do we do that? We have this ready-made sequence here. In order to show it's not sequentially continuous, we just need to find a sequence that converges to p, but if we apply f, it doesn't converge to f of p. But this sequence that we chose in this clever way will do the trick. Here's how it goes. Look at xn, and xn converges to p because I'll just do it here, because how do you show something converges to p? You just let epsilon greater than 0 be arbitrary, and then choose, say, a natural number n to be bigger than or equal to 1 over epsilon. Then we have whenever n is bigger than or equal to n, but the distance between p and xn is less than 1 over n, which is less than epsilon. So okay. So I mean, although it's intuitively clear, if you want to write it down, you can just write in this fashion. So we have a sequence that converges to p because we chose the distance between p and xn to get arbitrarily small. So we have xn tends to p. However, does f of xn tend to f of p? Well, if f of xn tended to f of p, then no matter what epsilon we chose, we should be able to go far enough down the sequence that these two would be close to each other. However, we know that the distance between f of p and f of xn is always bigger than or equal to this epsilon. So no matter how far down we go, we won't be able to be smaller than epsilon. So f of xn does not tend to f of p. So you found a sequence that tends to p. If you apply f of xn, then it doesn't tend to f of p. So it means our function is not sequentially continuous at f of p either. So not continuous implies not sequentially continuous, which is the same thing as saying sequential continuity implies continuity, and that is how the proof goes. I look forward to seeing you in the future video. Bye.